Hi guys, this is Faizan and welcome to today's session on Introduction to Recursion by Great Learning. Now before I start, can you guys quickly confirm if I'm audible, is my slide deck visible to you guys, is the pointer visible to you guys? If everything is good, just give me a quick confirmation in the chat. While we wait for others to join, let me give you a quick tour of how our academy looks like. So go into your browser, type in Great Learning Academy, the first link that is here. Just click on it, it will redirect you to this page. And in this page, you have something that is career path. If you're looking for IT and software, just click on software developer and just sign up. Okay. And if you're looking for transformation of your career, right, we have programs associated with them. Okay, so the popular courses are, if you talk about software development, we have some courses out there: advanced software engineering, IIT Madras, triple IT Hyderabad, triple IT Hyderabad, right, and the MCA degree program is also there. If you're looking for something that is related to data science and business analytics, we also have PG programs available. Okay, now if you talk about some of the free courses, right, that are there, free content that is available, wherein you also get the completion certificate. If you're looking for something that is related to IT and software, right, we have courses available on them as well. Data structures, algorithms in Java, Java programming, cyber security, ethical hacking is there, front end development, HTML, CSS, blockchain, right, all of these courses are available. If you're looking for something that is in Hindi, right, we have courses available in them as well. We have Python programming in Hindi, we have machine learning in Hindi, Java programming in Hindi, C++, React. All these courses are absolutely free. And in order to get the completion certificate, right, you just need to answer 6 questions correctly out of 10. Okay, cool. And if you're looking for live sessions that are there, today I'm taking this introduction on recursion. Then we have tomorrow on Sunday, we have from 6 to 7 we have DevOps, right? What a cliche, that is the name of the session, right? IT and software tomorrow related to Python of different job roles, Python for different job roles. It is on Tuesday 30th March. Okay, so do check those sessions and let's get started with our session. Okay, cool. So today we are going to talk about what introduction to recursion. I can see some yeses. Okay, cool. So today we're going to talk about introduction to recursion. So first, let's understand what is this recursion. So if you talk about recursion, what is this? So you might be knowing these things. Okay, when a function is calling itself, right, again and again, that is what a recursion is, right? It's very intuitive when you know that your problem is can be broken down into sub problems. Okay, so what do you mean by a sub problem? Let's suppose you just talk about factorial of a number, right? Fact 5, that's the name of the function f, and you're talking about factorial 5. Now we know that in order to calculate the factorial 5, we should know the factorial of what, 4. In order to calculate that, we should be able to know factorial of 3, and so on, right? So when your problem can be broken down into sub problems, at that time you can think of recursion. And there are many data structures which are recursive in nature. If you talk about trees, right, if you talk about graphs, therein the best approach is to use a recursion. If you talk about traversals, level traversal, inorder, inorder traversals, right, we have preorder, postorder, we have breadth-first, BFS, DFS, all these traversals. Recursion is one of the most naive and most easy way to traverse through a tree by using recursion. Okay, so this is what a recursion is. Now let's dive deep into it. Okay, so in recursion, there are 3 conditions, right? So there are 3 things that you should look for. Okay, the first thing is that obviously there should be a function, and if it has some arguments depending on that, let's suppose there's int n, and then you don't call your function again and again. And if there is no base condition, right, if this condition is not there, what is this base condition which tells this recursive function to stop? Okay, so this will tell you, okay, stop now, don't go for ahead, right? So now what is this? When you're calling this function and this time around on a less number, for example, let's suppose you have a function here and this is a recursive function and you want to print numbers from, let's suppose, I have given you 5 and I want to print them 5, 4, 3, 2, 1, a simple algorithm, right? I want to print these numbers. I gave you 5 and I want 5, 4, 3, 2, 1 to be printed. So what you will do, you will say, okay, when the n is equal to, when this n is equal to, let's suppose when this n is less than 0, okay, what you will do, return. You will say return. Let me just write these things again. You have this function over here which takes in an argument n. Now what you say, you said okay, if n is less than 0, then return. Else what you do, just print SOP, or you can use printf, anything, right? SOP, that is system.out.println n, and then what you say, okay, now once that is done, call this function again, but this time on n minus 1. Okay, now let's break down these things. Okay, this, okay, when 5 is inputted, the argument n is equal to 5, right? Now it checked, okay, is n less than 0? No, it is not. This won't be executed. Just print out 5. Return, 5 is printed. Then this time around it sends 4 to this function. Now 4, it checks again, so prints 4, then sends 3, then sends 2, then sends 1. Once 1 is set, it will check, okay, no, print. Then 0 is sent, and this time, or you can say they're less than or equal to 0. This is the condition, this holds, and it returns, right? Done. This is a simple recursion, or you can say simple algorithm in which we are using recursion. Now let's try to break down these things, right? What are these things? What a base condition is, what a logic is, and what is a recursive call. So if you observe carefully, here we have all these things available, right? And you just erase all those other things. Okay, now let's see what is a base condition. So this is your base condition. This tells your program, okay, or your function, do not go ahead. If this is not present, then there will be an error which is known as stack overflow. That means you are just piling up. Because why stack overflow? You might be thinking, okay, so why stack overflow? Why not something else? Because internally, I will show you what this recursion uses is stack. Okay, I will tell you, I will give different examples wherein I will also show you the actuation record which is created wherein this stack comes into picture. Okay, so don't worry about it for now. So this is the base condition. If it wouldn't have been here, we will get an error. Then what we are doing, we are telling him, okay, print this statement. Done. He printed it, and then this is your logic. This can be any logic, right? This time around it is very simple logic, so I'm just printing it. Then is your recursive call. This is your recursive call. Okay, done. So these are your 3 major steps. Okay, and you need to keep a good. You need to know all these things, right? What is your logic? What are the things that you're going to do in that function? What is your base condition, so that you know when to stop, and then the recursive call. Okay, done. So these are the steps that are required. Now what else is there? Now let's understand first why recursion, why not iteration. So recursion is about function calling itself, we know that, right? Whereas iteration can't call itself, right? Iteration is simply if you have a for loop and then you're traversing from, if I want to do the same thing, right? I want to print, we have n equal to 5 and we'll say n less than or equal to 0, I plus plus. Okay, unless and until this condition is not false, what we do, we'll just print out our n. Not I plus plus, you will say I minus minus, because we are printing. So this is the iterative program for the same which we used earlier, right? So same thing, right? But what happens in iteration, let's suppose I told you to traverse through a tree. At that time, iteration becomes much more complex, and we'll see how easily we can solve. I will give you an example wherein we will say, okay, binary search. If we talk about binary search, we can apply normal iterative functions, like we can use a while loop and do the thing, or we can use a recursive call. I'll show you in this session itself how can we solve that using a recursion, the binary search thing. Okay, now when you talk about space complexity, obviously there is no space associated with this, right? Because you are not using any extra space. Now what is the space complexity? If you have an algorithm and in that algorithm you are not using any extra space, and that extra space can be in the form of what? A string, wherein you're storing these n number of wherein you have the length of that string is n, that is 5. It can be an array, it can be an array list, it can be a linked list, it can be a stack, it can be a queue. So all of these, whenever you are using these extra memory, that is where your space complexity comes into picture. As I told you earlier, right, when you are using recursion, there is something extra that you are utilizing, that is the space. But usually there is a trade-off between time and space, and usually space is ignored. And if Space is not ignored, it will be specified in your question. Please take care of space. That means I want a space efficient algorithm, not time efficient. At that time, there's a trade off. Trade off means either go for space efficient or go for time efficient. So that thing is always there. Okay. So recursion internally uses stack, that is the memory or the extra memory. But there are some recursive calls in which this stack, even if you're using stack, still the space complexity is constant. I'll show you those things as well. Okay, don't worry about it. So now these things are done, right? And recursion is implicitly works with stack, as I told you earlier, right? There is no such requirement in the iteration, as we saw. The same program for recursion, wherein we are using extra space, and this is the for loop within which we are doing the same thing, but no extra space. Recursion is slower than iteration because a stack has to be maintained, right? So now with all these things, you might be thinking, okay, iteration is easy and it is easy to implement, but recursion is much more intuitive when you talk about some data structures, or if you have some different examples at that time. Recursion is much more intuitive as compared to iteration. Okay, so let's move ahead now. What else? Now let's understand. I told you that internally a stack is maintained. Right now, let's see when that stack is maintained and how that stack works, and what are the different types of recursion wherein that stack, even if we have a stack, still we will be using only constant amount of space. That means it is same as if you're using something. Let's suppose I gave you an example, and you are maintaining a stack, or you are maintaining an array list wherein you are storing a, e, I, o, u, that are the vowels, and I gave you a string, and that string can be of any length, right? I gave you a string or a character array. Let's suppose a character array of size 100. There are 100 characters. Now I want you to exclude these a, e, I, o, u from that string. So even though you are using this stack or array list or anything, right? You are using this array list or an array, right? Still this space will be considered as constant. Can anyone tell me why? So we have participants. Can anyone tell me why, even if we are using this extra space or for storing these 5 characters in an array, still the space complexity will be 1? Why? Can anyone tell me in the chat? You can write it in the chat quickly, guys. Anyone? Can anyone answer this question? So basically, even whatever is the situation, right? If you have a character array in which the number of elements or number of characters is 100, still you're going to store only these characters in your memory. That is, you're going to use only 5 extra spaces, or you can say array of size 5. If it is 10,000, still you're going to use this 5. If this is a million, there are a million characters, still you are going to use these 5, because there are only 5 vowels, right? So even if now you have to be very you have to be very open-minded in terms of what you say whenever you're using this extra space. It's not always that whether you use any extra space or not, still there are cases wherein these are considered to be a constant amount of space, because it is independent of number of characters that are there in our input array or input character array. Okay, done. So now let's see what the types of recursion. So tail recursion. The recursive call is the last step of the implementation, like we have seen in earlier. If n is greater than or equal to 0, return. Then we had SOP, and then the recursive call is the last step. That is, this was the recursive call wherein we were calling function fn, right? So this was the last step in the recursion. Now there are no statements to be executed, right? So this is your tail recursion. Whenever your recursion has, or you can say that the recursive call is the last step and you don't have any statements to be, there are no statements after this. There is no activation record that has to be maintained. So this is your recursion. That is known as tail recursion, and it is a faster approach of recursion. Whenever you want to reduce the space complexity, you can go for what tail recursion, right? Now whatever was there in the space, whatever you say that, okay, you might say that, okay, the recursion is you have to use an extra space. But if you can convert your code into tail recursion, good, there is no extra space in it. Okay, done. Let's give an example. Let's take an example, same example. Okay, void fun int n. If int n is less than or equal to 0, what do you say? Return. And then what are you going to say? SOP n, and then again function is calling itself. Done. So this is your tail recursion example. Simple, right? Now if you say, what is this activation record, sir? We don't get it. What is this activation record? Let's name these statements. Okay, let's name these statements as 1 2 3 4, so that it's easy for me to create an activation record. Let's suppose this is statement 1, this is 2, and this is 3. Now what is an activation record? So let's create an activation record. So this is your activation record. That means the first function, that is the main there, will call this function. Obviously the driver function will be there, which calls this function fun, and it sends in the argument as n. So now for n equal to 5, so this is our f5, this is our activation record. First statement, it checks it, done. Second statement, it prints it, done. It prints what? 5. Okay, so there's a difference, Abhishek, between int fun. If you're saying that why not I'm returning any value, you see I haven't written any value over here, right? I haven't written any value over here. It's return, just the return. That means pass in the control, not the value. So that is why it is void. Okay, so this is also done. 5 is printed. Then you have your function call, that is f4, that is it's calling the function. Now there are no statements left, so it will be popped out of the stack, and we will have again, this will be popped out, and we will have the function, we'll have the what you say, activation record, which is for function f4. This will be popped out, so you're not using any extra memory. You are performing all of these operations on the same call stack, or you can say activation record. Okay, so now again it will check 1 2 3, execute it, 4, print it, and then call it again on f3. Again this will be popped off, no statements are left, done. So you see the space has been utilized efficiently, and this is a space efficient algorithm because you're using constant amount of space. Done. This is your tail recursion. Now if we have a scenario wherein this recursive call is not the last step, again the same algorithm, right? You have function int n. I will change one single statement, that's it. If n is less than or equal to 0, please return, else whatever you want to do. Call this recursive function again, and this time on f is on n minus 1, that is 5. Now call it on 4, then print. Now you have this SOP statement at the end. Now this is your what, program logic, or you can say the recursive logic that is there. This is your recursive call, or you can say it's also the self work, that is whatever you are doing, self work. Okay, recursive call is here, and this is your base condition. Now this is a slower approach, as you can see, because we have to maintain the call stack, right? And now if that call stack has to be maintained, there's an extra space that you require. Okay, now let's see what is that activation record, how it looks like. So let's take an example. Void fun int n, right? Say if n is equal to less than or equal to 0, return, else what you will do, you have this function call for n minus 1, done, and then you have this print statement over here, right? Now let's create an activation record and see how things will work, how things will go. Okay, let's create an activation record. So this is your activation record for function f equal to 5. Now again I'll name these statements as 1 2 and 3, done. These are your statements. Now first step, execute it. Second, it will call the function for f equal to 4. So now this third statement that is there, it is left behind. So again an activation record will be called. Activation or you can say the stack will call this thing, and it will just push it on top of this. So you will call it for 1 5 1 equal to 4, that is function for 4. One is statement is executed. Second, again it will be called for f3. Okay, again an activation record will be called, activation record will be there. Then this third statement will be left for execution. One, done. Second, again it will be called, and so on, right? Now let's suppose we don't want to go further, so let's change this to 2, or let's change this to 1 is less than or equal to 1. So this is called, and then the function call will call for 1. Now what happens over here? Now this is the thing, this is the most important thing of performing this recursion call. So third statement is left, third statement is left over here, over here, over here. What's third statement? This third statement, because recursion was called before that. Okay, this is a non-tail recursion. Okay, now once the function for function with arguments 1 is called, we check, okay, this is less than, no, this is equal to 1, so return. So now this first statement will make this function to return. Now this is implicit, or you can say that this is explicit, that you are explicitly returning the function, or you're returning, you're saying, okay, don't go further, just return. Okay, done. Now after that, all of the recursions will be implicit because there are no statements to be left. So this will be an implicit return, automatic return, you can say. Okay, now the third statements will be executed. What are those? And please print SOP, that is SOP means system.out.println, n, please print this n. So what is the value of n? It is 2. Print it. Done. Now there will be no there are no statements left, it will return over here. Now again, print n, 3, return, implicit return. Okay, that is why we have a void return type over here, not int or anything, right? Now implicit return, please print 4, done. Return, please print 5, done. Return to the main function, that is your driver function, done. This is your non-tail recursion. Okay, now we have one more recursion, that is direct recursion. When we have seen this example, when a function, that is this one we talked about, calls itself again, and both of these functions function calls, that means in the same function we are calling the same function, and it is called within the same function, right? Only, and we have only one function that is involved. So this is your direct recursion. Okay, example can be this, which we were talked about earlier, right? The same example which we talked earlier, again and again, right? So there's a function n which is calling again itself, done. This is your direct recursion. Now if you talk about indirect recursion, what is that? So you have a function, and that function you're calling some different function. Okay, and then that there's a function which is calling that function. So you see there's a dependency. So we have a function 1, or you can say fun1, which is calling fun2. That means this function fun2, and inside this you have fun1, which is this function, you're calling this function. Okay, done. So this is what is your indirect recursion. So there are more than one function involved. So you have two functions. This is one function, this is one. So you can have, here I'm giving an example wherein only two functions are there. You can have more than two functions as well. If you talk about an example, let's suppose we have an example over here. We have a function named print. Okay, now print, in this we are calling another function evaluate. Okay, now once whatever is the base condition and all those things. Okay, now this function called evaluate is over here, and it does the evaluation and it calls the print. So whatever you are evaluating, call this print. Once print is done, call this evaluate, print, unless and until we reach the base conditions of both these functions. Okay, done. So this is indirect recursion. Now if you talk about time and space complexity, it again depends on algorithm and algorithm. Okay, if you talk about this algorithm wherein we just printed 5 to 4, right? Similarly we can print from 1 to 5. So we are only calling this function once, right, in our program, right? So you have a recursive call is called 5 times. Depending upon this n, this recursion is called. Okay, so in this recursion, if you talk about this recursion, this time complexity is big O of n. Okay, it is not that always recursion will have those exponential time complexities to raise power n, which we have already seen when you talk about what factorial of a number, right? So, or when you are trying to find a Fibonacci series, therein when you have two functions depending upon what is a Fibonacci series? Nothing but this 0, 1, 1, then you add these two, you get 2, then you add these two, you get 3, then you add these two, you get 5, and then so on to 8. So if you talk about the recursive call that is required in Fibonacci series, right? 1 2 3 5. You will say okay, you have one function which is taking an argument as n, and then whatever you want to do, if n is greater than 0, return and all those things. But there will be a function which says that return function, you add up these two, right? N minus 1, because this is this, if you want to evaluate this is dependent on this and this, so n minus 1 and n minus 2. Okay, and you will also check if n is equal to 0, that means this condition, return n, or if n is equal to 1, return n, right? Return, in both these cases, return n. So these two cases are solved. So this is how you execute, or in this case, since there are two recursive calls that are happening, so in this case it will be 2 raised power n. Okay, so yes, Swapan, we have a data structure in Java that is available on our Great Learning Academy. Plus we have a full course on data structures and algorithms, which is for almost 10 hours. Okay, you can check it once the session is over. Okay, done. So this is your recursion, and this is the time complexity I was talking about, 2 raised power n, whenever your function gets broken down into two subparts, right? Similarly for binary, we have a left subtree wherein these recursive calls happen, again 2 raised power n. Okay, so this is all about time. Now we already have discussed this, whenever you're trying to store, or whenever you have an activation record wherein you're storing the number of items, right, that are there in the, let's suppose you want to print n elements, and you are storing there, you have n activation records, so you will say the space complexity is big O of n. And if you are using tail recursion, at that time this will be reduced to constant, right? So this is the space complexity. Whenever you are having different algorithms, it will be different for different algorithms, right? So is this thing clear, guys? Quickly confirm. Am I going too fast, or is this thing clear? Do you want me to repeat anything, the time, the space, or this indirect recursion, direct recursion, tail, non-tail, how they are different, how we are utilizing the space in both these things? Okay, so please confirm, and if everything is okay, you are able to understand, great. So we'll move ahead with the examples and we'll see more. Quickly, guys, just confirm in the chat if I'm audible, if you were able to understand all of these things, right? These things are dependent, or these things keep on changing from algorithm to algorithm. Okay, quickly, guys. Okay, others says okay. Yes, Prashant, we have an Angular course as well. So let's talk about this time and space complexity again. So now let's talk about time first. Okay. So as we talked about this simple algorithm, that is okay. Let's do one thing. Let's try to think of space and time complexity with this example. Okay. So now let's talk about this example and try to understand these things, space and time complexity over here. Okay. So now you have this example over here wherein we are declaring a class TL node, that is tree, and in that tree you have a data part and you have the left and the right. Okay, so you have like this is your tree node. Structure of that node is like this. So this we are talking about here, binary tree. Okay, so now we have this is the structure of that node. Okay, so now you have a data part and you have your left, you have your right. Okay, done. So now you also have a constructor which is used to set up this data. Done. Now you have a class that is named as binary tree, right? And in that we are just using these functions. What this is a preorder, and we will talk about it once we have our main. Okay, so now in our main, what we are doing, we are creating an object and named this basically the reference variable, that is root, and we are passing in an argument as 1, so that our constructor, what he does, constructor instantiates, or it is in this constructor, what it does, it sets up the data part, okay, of this node. Okay, done. So now what we are doing basically, let's go back to our main. We have this node over here, right? And then this left part is null, this is the left null, this data is 1, this is also null. Okay, this is your this done. Okay, now what we are saying, we are saying that roots left, this is our root, right? Roots left, we are talking about this. Okay, so now what we are saying, please go ahead and insert or create a node, and whatever is the reference of that node, please insert that thing over here. Okay, what is the reference? So what we did, we created one node with the data part as 3, and this is also null, this is also null, and whatever was the reference of this node, that is stored over here. Okay, let's suppose it is a hexadecimal number, the reference will be a hexadecimal number. For simplicity, I am taking this as 1000, so 1000 is over here. Similarly, what we said, please go ahead and do the same for write as well, and this time around store, okay, this was 2, right? This was 2. This time around, go ahead and store what? The value as 3. So this is 3, this is null, this is null, and we have some reference over here. Let's suppose 2000, and that 2000 reference is stored over here. Okay, now I'm also creating it in this way, but I will also create it in different way over here, right? So you have this node 1, and have a left subchild, and it will have a right subchild. Done. Similarly, it will say go into lefts left. So go into lefts, that is, we're talking about this, and left is this, we're talking about this left. So another thing, there will be a left of this, and we are storing what? 4, and in his right store 6. So this is 6. Similarly, go into the roots right's right, that is roots right is this, we're talking about this, store some value. So this is null over here, and this will have 7. Okay, done. This is the tree that we just created. Okay, now what we are doing, once we have this tree in place, what we are doing, we are going to calculate the pre-order, the in-order, and post-order. So this is a binary tree, not a BST. Okay, BST has to follow some structure, that you can only insert elements that are on the left side, you can only store the elements that are less than this, and on the right hand side you can only store the elements that are greater than the root. Done. But this is a simple binary tree. Now let's try to calculate on the same tree, we try to calculate the pre-order. Okay, so let's clear the screen, and you see what are the things that we are going to use. Okay, so now what we are doing, this is our tree, 1 2 3 4 and 5, and then we have 7 over here. Done. So now what we are going to do, we have this pre-order, that is the function that is called, and we are passing in the root. So this is passed, the reference of this node is passed. Okay, clear? Now let's think about those 3 conditions that will be always there in a recursion. So this is your what? This is your base condition, right? This is your self work, or you can say the logic, and these are your recursive calls. So you can see that there are 2 recursive calls. Okay, so now let's understand how this pre-order works. So pre-order is a function which, or you can say it's a traversal, that we want to traverse through this through this tree, that is this binary tree. We want to traverse means printing out or evaluating whatever is in the data part of these nodes. Okay, so we want to traverse, or you can say that we want to go for this node, then this node, then this, then this, then this. We want to traverse each and every node. For that, this is one of the traversals, that is pre-order. What it says, that go on this node and print its data. So 1 will be printed. So this is the self work, and we printed out the data of this R, because I told you this root is shared with us, the root node. So this is our root node for now. Now what we are doing, we are printing out 1, then recursively we are calling this pre-order, but this time around we are sending the roots left. So we are talking about this, and for this function, that is the next function that is called, this will be the root. Okay, this is very, very important, guys, and most of the questions can be solved with the help of these traversals when you're talking about competitive programming, and there is a question that is related to what? Trees. Okay, almost most of the times. Okay, now what is happening for this recursive call? This is the root, and now we are checking, is this root equal to null? No, base condition is not met yet. Now what we are going to do, we are going to say, okay, print its data. So 2 will be printed. Done. Now again, now you see this function is called, right? This function is still left for this. So we'll write P, that is print left and right. So P is called, left is called, right is still left. Similarly, P is called, that is printing is done, left we will call the left, and this right is yet to be called. So again we are calling this, we will reach here, and for this will be the root, that is we are passing. Yes, you can do also string permutation, right? So similarly you can do any combinations, right? String permutations can be solved. If you want to solve more efficiently, you can use dynamic programming, Abhishek, right? So now what is this? This is the root, right? And now what we are going to do, again we have print left and r. So print the root, that is print the 4, go for the left, it goes for the left, and this time around it will be null, so it will be, the base condition will be met and it will return. So it will return to its caller, that is this function. It will go on from the right hand side, it will execute, there is nothing, null, again base condition will be met, it will return. So all the function calls for this particular node is done. Okay, so all the function calls for this node are done. So let's write this here. So P was checked, printed, left and right, all of these were done. So now this is earlier there was, this is known as an explicit return that we did once the condition is met. Right now, once all the statements are done, it will be an implicit return to the caller. Who was the caller? This was the caller. Now printing was done, left was done. Now this entire left tree is done. Now we have this right side that was yet to be traversed, right? So it goes to the right, right? And now print left and right. So printing will be done. 5 is done. It goes from the left, null. It goes from the right, null. Comes back and does nothing. All the function calls are done. It will return to the caller, that is this. And it will now go on the right hand side. Right hand side done. This side again left, print left and right. Print 3, go left, nothing. Go on the right, done. Print left, right, go on the left, nothing. First print it, right? Print, go on the left, nothing, return. Go on the right, nothing, return. Now once all the statements are done, return to the caller. No statements are left, return to the caller. No statements are left, return to the main function which called it. That was our driver function, right? So this was the output of this particular tree. Okay, now let me give you an example and I want an answer from you guys. Okay, so let's clear the screen and let's write it. Okay, create a tree, 10, 20, then you have 30 over here, then let's suppose you have 8, you have 6, you have 4. Okay, so now try to calculate this and what will be the answer quickly, guys. What will be the output when we call, this is our tree and we call preorder on it? Quickly. What will be the output? Quickly, guys, any one of you? Quickly, anyone? So again the same thing, you have to follow the procedure that go on the left, print the data, go on the left, go on the right. Okay, so trend will be printed, it goes here, it checks, 20 will be printed, it goes here, prints the data, 30 will be printed, it goes on the left again, right? It will print 8, yes. Okay, 30, Abhishek, there's a issue in your output. So 30 will be printed now. So print left and right. So print will be the first statement. Whenever it goes on this node, it will print it. Then 8. Then it goes here, prints the 6. Then it prints the 4, right? So this will be the output. Okay. So 30, then 8. Right? This will be your output. Okay. Done. And similarly, we have functions that are available. Okay. Now similarly we have function available that is inorder, which works in such a fashion. Okay, yes, 10 20 30 864. Yes, 10 20 30 864 exactly. Yeah, 8 and 30, not 8 and 30. Yes, correct Kashyap. Okay, done. So now if we talk about this in order, so in order, whenever you are in a particular node, it will work in such a manner that, let's suppose this is your node, and it will work in such a manner that first, in order means that whatever you are doing, the printing statement will be in the middle. So go on the left, print, and then go on the right. So LPR. Earlier it was PLR, print left and right. Now this time around it is L, that is go on the left side, print the data, go on the left side, print the data, go on the left. Okay. So now how it works? So we have LPR, right? So we have L, P, and R over here. So it will go on the left, L, P, and R. It will go on the left, L, P, and R. So in this case, this is the first element that will be printed. Okay, is this thing clear? And similarly, you can go for post order. Post order means L, go on the left hand side, left child, that is the left child, go on the right child, right, and then print the data. You see, the ordering differs here. So you have two function calls, and this is kept at the end. So this is how you traverse. So these are the three traversing algorithms that you can use. Do you have anyone understanding? Okay, so now these are your traversals, three traversals. Now whenever you have a binary tree and you are asked to traverse, so you can traverse it with the help of what? First is the in order traversal, then you have post order traversal, pre-order. You can also traverse with the help of BST, or you can say BFS, the breadth first search, that is your level order, breadth by breadth, and then DFS, you go into the depth. Okay, these are all the sections, all the traversals. Okay, now let's take another example. So binary search. Now we all know when you talk about binary search, right? So whenever you have an array, right, in that array, this will be a sorted array, right, and you want to check whether a particular element is present in the array or not. Okay, so if you go for a linear search, right, you are linearly searching in the element. What you will do, you have a pointer which will or the iterator which will traverse one by one to all the elements, right? So it will check, okay, is this the element? No. Is this the element? Is this the element? Is this the element? Is this the element? No, it is not. So now this is the linear traversal, and the time complexity will be big of n. And if you talk about space, because you're traversing all the elements once, so the time complexity will be big of n. And space, you're not using any extra space. Are there C++ classes? Yes, there are. Okay, and we do have a sessions on C++, and if you want to learn, we do have courses available on our Great Learning Academy. You can check it, okay, once the session is over. Okay, so now if you talk about space, big O of 1, right? Now this was not the efficient algorithm, right? We came up with an efficient algorithm, that is the binary search. Now binary search can be implemented with the help of iterative algorithm or with the help of recursive algorithm. Now how binary search works, let's suppose this is your array, and you want to, let's suppose you want to check if 5 is present in the array or not. So what binary search does, it divides your search space every time into two equal halves, and at least it tries to do it in two equal halves, because right now there are 6 elements, it will divide it into 3. If there are 3 elements, it will divide it into 1, and one side will be 1 and other side will be 2. So it will try to divide it in two equal halves. Okay, so for 6 it was easy, 3 right, and for 3 it's difficult, so 1 and 2. So for this one, if that is not the element, so it will go for here, then it will divide it into 2 parts, 1 and 1. Okay, so this is how it works. So let's try to calculate all the things that are there in this function. Okay, the recursive function that we have over here. So again, there will be a base condition, or whatever we are doing, we will do it unless and until we have beginning is less than end, right? We calculate the middle, we check if we have found the element, right? If we haven't found the element, we will divide the array into 2 halves. This is where our recursion comes into picture. We are recursively calling this binary search algorithm or binary search function, and then again we are recursively calling it on the other half if this condition is not met. Okay, cool. So now let's see how to divide this thing. Okay, so we have an array over here, right? 1 2 3 4. Okay, okay, 1 second. So let's clear the screen and let's try it again. So this is the array: 1 2 3 4 5 and 6. So you have item that you want to search. Let's suppose we are searching 5, and this is the beginning index, which is 0, and this is the ending index. So 0 1 2 3 4 and 5. So this is your ending index. Okay, now you have also passed in the array. Now what is the first step? Can anyone tell me what is the first step that you will do? First you will check if beginning is less than or equal to end. So this is 0. 0 is obviously less than 5. So what you will do, you will calculate the middle index. What will be the value of middle index? Can anyone tell me what will be the value of middle index? Quickly, guys. Quickly, can anyone answer? So the value will be simple: 0 plus 5, that is 5 divided by 2, and it will truncate the 0.5 part, and the value will be 2. Okay, so this is your middle index. So 0 plus 5, that is 5, 2.5, and 2 will be truncated. Okay, let's clear this thing. Cool. Now once we have this, okay, middle index, now what we are going to do, if we are looking, now this array is sorted, if we are looking for 5, will there ever be the case that this 5 will be on this side? No, right? Why? Because this array is sorted and we have the middle index that is pointing to this 3. There is no chance that we can have this index element 5 that is present, that can be present on the left hand side. There will be no chance. So that is how we can ignore this part, and we can be sure that the element will not be present on the left hand side. So what we do, first we will check, okay, is this the element that we are looking for? Is this the 3 that we are trying to search? No, the item was 5, we were trying to search for 5, so this is not the item. Had it been the item, so done, this would have been done in a constant amount of time. Done. That is the best case when you're trying to find any algorithm, or when you're trying to find any element in the array. Okay, now once this is done, now what you will do, you will check, okay, are you going to neglect this part or this part? That is your middle index. Are you going to neglect this part or this part? Now how to do that, how to make that decision? With the help of this thing, okay, you will check if the item that you have, that is 5, if it is less than the array index, obviously. Now this 5 is not less than, it is not less than what you can say, is not less than 5 is, okay, just let me erase these things. Obviously 5 is not less than 3. So what you are going to do, you are not going to execute this statement. Okay, the statement will not be executed. Else what you are going to do, since we know for sure this 5 will not be on this side, now we will update our middle index, or we can update our item. Okay, so what you will say, will say, now the beginning is now pointing to this, we'll update it to middle index plus 1, right? So this will be our beginning, new beginning, that is pointing to index 4. Okay, so if item is less than, we will say, okay, it should be if item is greater than. Okay, so this will be executed if item is greater than middle index. So what you will say, update the beginning, right? Update the beginning. Let's clear this screen. Now we'll update our beginning. Okay, earlier our beginning was here, end was here. Now our middle index was here. Now we'll update our beginning to middle index plus 1. So this will be our new beginning, and we will recursively call this function again. Done. Now what is happening? Now again we'll check, is our beginning less than end? Yes, it is. Beginning is what? 3, end is 5. Now we'll see, we'll again calculate its middle point or middle element. We will say 3 plus 5 divided by 2. That is 8 divided by 2, that is 4. So your middle index is this, middle index. Okay, done. Now we'll check, Is this middle index our element that we're trying to find? Yes, it is 5. We were looking for 5. That was the item that we were looking for. What you will say, okay, do not move ahead, just return whatever is the value. So we returned the middle index. Okay, so now once we are returning it, none of the statements will be executed. Done. This is how you find it. Within at worst what you can say that whenever you're talking about binary search, if you talk about the worst case time complexity, I told you that in the best case that this is the middle index and this was the element you were trying to find. So the best case time complexity will be big O of n, and the worst will lie somewhere around big O, somewhere around the average, or you can say average case will be big O of log n by 2. So since these constant terms are ignored, so it will be again big O of log n. Now what is the worst case? How you can find out this worst case? Let's suppose if you have 8 elements, right? If you have 8 elements, what is the value of log 8 to the base 2? What will be its value? If you calculate this will be nothing but log 2 to the base 2 raised power 3. Now this is m raised power n. It can be written as m into n. So log 2 to the base 2. This is 1, and it will be, you will be able, now you calculated this thing, right? This is the assumption that you do. Okay, let's find out the value of log 8 to the base 2. It came out to be 3. So now you can be sure that if your array has 8 elements, let's suppose 1 2 3 4 5 6 7 and 8. Now first time around what will happen, you will calculate its length. It will be 0 plus 7, that is 3.5. so 0 1 2 3. So this is your middle index. Okay, now what will happen, this is the first now you will perform the first iteration. Now first iteration is what? So let's suppose you are looking for this, you are trying to find out this 8. Now first this is the first iteration that you will do, first recursive call that you will perform. So this is the middle index, right? And now you will find what? This will be a new beginning, that is 4, and this is 7. 4 plus 7 is 11. 11 divided by 2 is 5.5, and then it will be 5. So index will be here. This is your second recursive call. Now second time around, or you can say the third time around, this is nothing but your index 5. So 5 plus 2. So these are the indexes, 5 plus 5 6 7. Okay, so 5 plus 7 is 12. Again 12 divided by 2 is 6. So this is the second recursive call. So first recursive call, second recursive call, and third recursive call. In 3 recursive calls, you were able to find this element, that is 8, which is present at the end. So in the worst case scenario, the time complexity of this algorithm is big O of log n. What about the space? Since we have both of these recursive calls, right? Both of these recursive calls at the end, right? This is the recursive call. No statement is to be executed because this is an else. So if this is executed, this will never be executed. Okay, so if this is executed, this will never be executed. So these are the last statements, right? Remember the tail recursion. So since this is the last call, or you can say this is the last statement that is to be executed, the recursion is taking place at the end, and there are no statements to be left that has to be called after the recursion is done. So you can say that this is obviously tail recursion, and it will take constant amount of time. So you see the space and time complexity of this algorithm. Okay, so time complexity will be big O of log n, and the space will be constant. Okay, that is big O of 1. So this is how you perform. Okay, this is the algorithm of a binary search using recursion. So let's try to just reiterate what we learned. Okay, so first we talked about let me go back. Okay, first we will talk about what is a recursion. So recursion is nothing but a function calling itself. Then we talked about 3 steps, right? What are those 3 steps? Base condition, logic, and recursive call. So this logic can be said as what? This can be also said as self work. That is the work that you are performing in this function. Okay, then we talked about recursion and iteration, how iteration is not that much intuitive in certain cases, and how recursion is much more efficient when you talk about time complexity. Okay, when you talk about time complexity, you might be thinking, okay, this is much more intuitive when you can break down your problem into sub problems. Okay, when you see, okay, your problem can be broken down into sub problems, at that time you can use recursion. And it's not always that recursion will take extra space. We have already seen that. How? With the help of these types of recursion, that is the tail recursion, wherein this last step will be your, yeah, if you want to sort that at that time, the time the you should definitely, in order to obviously now Abhishek has had a question. Array should be sorted for binary search, while inserting and sorting could be n log n plus n. So instead of, whenever your array is not sorted, right? So obviously now binary search can be applied on in certain questions wherever your array is not sorted. Even though your array is not sorted, you can still apply binary search. Now I'm giving you the reference of one question. Please go and find it out. Okay, try to find out the peak of the element. Okay, you need to find the peak. Therein you will see, okay, you will see, is this array sorted? No, this array is not sorted, but still you will be able to apply binary search on this problem. You can check it after the session is over. Okay, so it's not always a mandate or a rule that array should be sorted, but yes, in this case, which on wherever we applied and we were trying to find the element, that searching, therein you should have this array sorted in order to find that element. If that array is not sorted, you should never go for binary search, because that will, what you will be doing, you will be first sorting the algorithm or sorting the array, that is n log n, and then finding the element in big O of log n time, right? So that is obviously, now this will be taken into consideration, because this is the as our input size will increase, these things can be neglected. So it's definitely, you should definitely go for a linear search, which is much more efficient than this. Okay, so it will take a linear amount of time. Okay, so linear search is much more efficient. So coming back, we talked about tail recursion, which in which we can use efficiently our space complexity. Then we talked about non-tail, which is obviously when the recursion is not the last step, it is the second last or third last step. That means, in short, not, this is not again a rule that it is, there is only one statement left. There can be many statements left after the recursion. So this is non-tail recursion, when the last step is not your recursive call. And this time around, there will be space complexity associated. Okay, then we talked about direct recursion. Then we talked about indirect recursion, wherein two or more functions can call itself. Okay, and that function, let's me give you an example again. So you have function 1, in this you are calling function 2, then you have function 2 in which you are calling function 1. Okay, done. And then we talked about we talked about time and space, right? Space complexity, how to calculate it. And it's not always a mandate that whenever you're using space, it is always a a linear amount of space. Even though we talked about that AEIOU example, wherein although I am using these elements to store, but it will not depend on the input size. Okay, if we have a character array of 1000, still this AEIOU that I'm storing in an extra space, that I'm using this extra space, will be constant, 5 elements. If the input size is million, again 5 elements will be stored. AEIOU, only the vowels are only still 5. So this is, I am using this extra space, but this space will be again termed or it can be said that this is a constant amount of space, because it's not dependent on the input. Okay. And then we talked about one of the examples, that we talked about the binary tree traversals, inorder, preorder, and postorder. We saw how recursion is used and how easy it is to traverse with the help of recursion. And if you're trying to do the same thing in iteration, there will be a lot of steps involved. Okay, and since we are using, in some places we are using this, in some places we are using the tail recursion as well. Okay, then we talked about the final implementation or example, wherein we talked about this binary search. Okay, done. So this is it from this session, guys. I hope you enjoyed this session, and I will see you in the next session. Okay, thank you so much.